When we measure laser power, the sensor absorbs the beam as the first step, thereby measuring it. The optical power in the beam becomes heat inside the sensor, and that heat, once we're done measuring it, must be eliminated. If the heat comes in faster than we take it out, the sensor will heat up and will eventually fail. For powers above a few hundred watts, water cooling is the usual solution. In order for water cooling to work properly, though, there are a few critical issues that must be considered. Issue number 1, water temperature and flow rate. Flowing water is, of course, the basis of how the water cools the sensor. The minimum flow rate, as well as the specified range of water temperature, are both stated in all specifications. In this example, the minimum flow rate at full power is 4.5 liters per minute. At less than full power, the flow rate can be reduced proportionately, but usually to not less than about 1 liter per minute. These two parameters are calculated to allow a maximum water temperature rise of about 10 degrees Celsius. It's important to note, as shown here, that water temperature must be stable. A change of as little as 1 degree Celsius per minute could cause unwanted heat flow in the sensor and cause fluctuations in the reading. It's that sensitive. We sometimes get asked about what happens if the cooling water temperature is below the specified 18 degrees Celsius. Sometimes the available city water supply is simply cold. There are two separate effects that one needs to consider. A, we don't want to get moisture condensation on the absorber surface. If the room air is warm and humid, but the sensor body is cold because of the cold water flowing inside, that could cause condensation which may affect the reading. B, if the room air is warm while the sensor body is cold, again because of the cold water flowing inside, this temperature gradient could cause heat to flow from the outside towards the inside of the sensor. This heat flow could cause a negative offset in the power reading, giving a reading that's lower than the true power. Remember that these sensors measure laser power by measuring the heat flow outwards resulting from absorption of the laser beam. Issue number 2, corrosion. There are occasionally instances of corrosion in our water-cooled sensors. As you can see in these photos, the effects on the sensor can be severe. We have taken steps to resist such corrosion, including using the most resistive type of anodizing and rounding corners that tend to serve as focal points for corrosion, but it still may occur under certain conditions. In very general terms, corrosion is a result of reactions among different ions present in the water circuit. The problems are usually caused by ions in the water. For example, chlorides, ammonia, dissolved oxygen, sulfates, and bicarbonates can all cause problems. Also significant is the pH of the water. Water that's somewhat acidic can attack the hard anodized layer protecting the aluminum water channel, exposing the aluminum to the water. This could open a door to possible corrosion. So if there are corrosion problems and you can control the water environment, we recommend using DI or deionized water, although plain city tap water is usually fine. We're also now testing a sensor with only copper and plastic parts in contact with the water. This solution gives hope of offering sensors that will be essentially immune to corrosion. Contact Ophir if we can help you with your application through your local Ophir representative or via our website.